So we know how to calculate characters for my internal plus space-time symmetry, right? And then IBP and equation of motion are taken care of. Okay, so now we are now ready to write down the plethysticks. So for bosons, my plethysticks will be phi, d, and r. The exponential of r equal to 1 to infinity phi d phi to the power r I r h r, right? So now this is the total plethysticks. This phi is basically scaled by this d to the power del phi, which is basically scaling dimensions, right? And this is the total character. And now if you remember, which was on that board and not now, but if it's in your copy, you can check that when we calculate the SU2L cross SU2R character, all the characters, there's a, in front of that, there's a d sitting corresponding to that field. For the scalar d to the power 1, for the fermion d to the 3 by 2, right? Right? And now that will be cancelled with this quantity when we take the invariance. Okay. And here Z are the basically the coordinates, cross coordinates corresponding to the internal symmetries. Okay. And alpha beta correspond to the space-time symmetries. So this is the total character of this quantity. Now for the fermion, we write down as a psi d r exponential of r equal to 1 to infinity minus 1 to the power r plus 1 psi by d delta psi to the power r chi r z r alpha r beta r. So similar thing as previously we have this minus 1 to the power r plus 1. So we have plugged in that statistics information. Okay, and we have this P4 d alpha beta inverse, which is 1 minus d alpha beta times 1 minus d by alpha beta times 1 minus d alpha by beta times 1 minus d beta by alpha. Right? This was my momentum generating function. Okay. So now let's take one explicit example with the standard model gauge group and the actual fields that we talk about. So what is my gauge symmetry of the standard model? E1y, SU2L, SU3C. Right? So now I am taking a warp doublet, okay, whose hypercharge I am assigning as 1 by 6, SU2 doublet, SU3 triplet. Right. Now let's see, for this particular field, if I can write down the character for all these symmetries, we know how to accommodate the other fields. Right? Remember how the plethysticks properties, the characters of those things will be added up because it's an exponential polynomial. So just go back to last lecture, there we have seen for multiple fields how to do that thing. So then what will be my U1 character? Z1 to the power 1 by 6, chi2 of SU2 will be Z2 plus 1 by Z2, chi3 SU3 Z3 Z4 will be Z3 plus Z4 by Z3 plus 1 by Z4. Okay, just follow the steps. First we identify what is my symmetry, what is the charge under this internal symmetry, okay, and then I am writing the individual character for individual group, right? Okay, and then I write down basically my total character chi q. What is this? This is the fermion, right? So how do I write down? 3 by 2. This is a SU12 doublet, right? So it will have a SU12 quantum number and SU2R quantum number is not there. So this will be half comma 0, right? So this is which one? This is basically my short representation character for this fermion, right? And then I define my chi q gauge. What is my chi q gauge? Product of these three. Okay. So total character is basically in this way you accommodate. Any question up to this part? Please let me know if you do not follow any steps. Okay. Okay. So then I should be able to write down the statistics for this q d to the power 3 by 2 chi q, right? That is my statistics, the function of that thing. So how do I write down? I write down as an exponential r equal to 1 to infinity fermion, so minus 1 to the power r plus 1 by r q to the power r by d to the power 3 by 2 to the power r, and then I have chi q. That's all. And this chi q will have how many torus coordinates? 1, 2, 4, and then for SU12 consider another 2, 6. That's all. Okay. Now, what you can do actually, you can try, for example, you take up quark, right-handed up quark or UCL. Okay. And then you just do that thing. So just identify. Once you identify the representations, what you will do? You first write down the quantum number. So singlet up quark is basically have a hypercharge, but this is singlet, but this is 3 bar, right? So now you remember that when you construct basically this character, and then one has to be very careful. For example, when you write down this 3 character, it doesn't matter for me whether I'm choosing this one Z3 or Z4. I'll get the same thing. But this will matter when I'm writing a character for 3 bar. So once you fix your Z3, then when you compute a 3 bar, use the same convention. Otherwise, if you change Z3 and Z4, you will get same character for Z3, Z4. So the conjugation property among different fields, that should be consistent by the consistent assignment of the torus coordinates. Okay, that's the mistake mostly people do actually, because there's symmetry between this thing. Okay, so then no, that's a conjugate of left-handed. That will be 0, half. That's all. So then basically here the coordinates will be alpha. That will be in terms of beta then. Because singlet you write down as a either right-handed or charge conjugation left-handed, which will transform eventually half comma 0 will transform as 0, half. Right? And then you use that character. So if you just permanently first write down the represent and then find out the character, that's all. Okay. So now I hope you guys can write down the statistics and the characters for these given representations. Okay. Now what is left is basically our what we have to calculate d mu E1y, and these are the things that already we have mentioned in the last lecture, so I am not writing. And then we have to introduce, and it is important to note down that whether this is E1y or E1b minus L or whatever, right? So the form of this d mu and d mu SU, they don't change. So that's why it is useful information, because once you write down the measure for internal symmetries, now when you are writing for the space-time symmetries, so what you write down? You write down d mu SU2L times d mu SU2R, right? So once you know the measure for d mu SU2L, this internal symmetries, you don't need to calculate the measure for this thing. Only thing you have to change the torus coordinates. So for example, you have defined the SU2 internal symmetry torus coordinates as a Z2. So when you write down this measure, you will write down in terms of Z2. But this you will write down in terms of alpha. This you will write down in terms of beta. But the functional form would be exactly same. Okay, so this, if you have to remember that things, this will be function Z1, this will be Z2, this will be Z3, Z4, this will be alpha, and this will be beta. But the functional form of this thing will be the same. So if you can relate this information, that will be more minimalistic. Once you calculate for d mu SU3, for example, now you have a flavor symmetry, let's say, SU3L cross SU3R, right? You don't need to calculate them separately. What you do, you change the coordinates. You define some different coordinates. Okay, so once we have this measure, okay, and then we write down the whole Hilbert series in the plethysticks and we get the answer, right? We get the invariant polynomial, yes.
That's the perfect class, but not for the.
No, I'm coming to that. Just okay. So now let me give you some more example such that it will be clear to you. So when okay, so when I have B mu nu, so okay, let me call it SU3 SU2 and D1y. Okay, so how does it transform? 1, 1, 0, right? But under SU2L plus SU2R, this transform as a, this I'm when writing in terms of dimensionality. Spin, if you write down, you write down as a 1, 1, but if you write down, so this is a, remember, this is not the spin, this is the dimensionality. You can write down 1, 1. Okay, so now if you do that, what you have to calculate this quantity? BL, which is 1 by R, BL to the power R, chi 1, 0, or dr. Right? So, when you are working in a SU2L cross SU2R basis, you have to define the characters for the left-handed objects and the right-handed objects separately. Okay, and that is true for the any non-zero spin. This is one of the examples of field tensor. Okay, and then you do that thing for the fermion and all those things. So that's why in the standard model, if I write down the whole plethysticks, how does it look like? It's a function of scalar, fermion. So this X is a notation that universally used in our effective field theory community as a field tensor. It captures basically B mu nu, G mu nu, W mu nu, whatever. Okay, but X generally when you define some kind of field tensor. Okay, so this X. Okay, and some torus coordinates are there which I'm not writing. This is basically exponential of, you can write down phi r equal to 1 to infinity phi to the power r by phi r times exponential psi r equal to 1 to infinity minus 1 to the power r plus 1 by r psi chi, and then we have an exponential all x or r equal to 1 to infinity x to the power r by r chi x. So total in the concept of standard model when I'm writing, so I'm writing the exponential of all the scalar fields, okay, sum over phi. For example, let's say if I'm working a standard model, how many scalar fields I have? One Higgs doublet, right? But you may be interested in, for example, let's say, okay, so let's say tomorrow we find out something new scalar fields, let's say singlet scalar, okay. Then, of course, you can understand that that new particle you have observed on shell, right? So that will be counted in your effective field theory now as a lighter degree of freedom, because your energy has reached to the level where you can produce that particle on shell, right? Then your SMAP operators will not be sufficient. You have to enlarge that set. How do you do that thing? What you do, you just use the same thing, only here you increase this sum not only for the Higgs doublet but also for the real singlet scalar. Okay, so all the additional scalar information you can dump here, this summation. Similarly, this is the standard model fermions, and what is this psi? Psi captures your everything, E, U, D, L, Q, dagger, dagger, L dagger, Q dagger, and so on. Okay. So now, why you have to put a double copy of that thing? Because there's left and right, that way you can define. And so you define all the fermions, okay, for left and right chiral, and then you define their statistics here. You take the field tensor. If you have a standard model, you know, you have a SU2, SU3 and U1. So this X is basically your B mu nu, SU3 G mu nu, and you have a W mu nu, and their left and right partners. So then you have written down everything here, right? So in this way, if you categorically write down different spin statistics, now you know if you want to calculate for, let's say, low energy effective field theory, right? So your low energy effective field theory have a SU3 C cross U1 electromagnetism, right? So then you just remove this part. You do not need any scalar there, right? So you have the fermions only, okay, and you have a field tensor for SU3 and U1. You just modify this accordingly. D is okay. You can D will be there because covariant derivative is there, which is corresponding to now your SU3 color and electromagnetism. But this there is no scalar at the low energy, so you can just remove this scalar part. That's why initially I told that though the construction I am doing keeping in mind about the SMAP, but this you can generalize for any connected compact groups, anything. For example, you are interested in standard model times some E1B minus L. You have some additional gauge symmetry, right? You just add one more field tensor, and if you have some new fermions or scalar, you just add them. So in this basis, you can just construct what are the field theory or the operators that you want to do. Okay? Yeah. Any question? Yes, yes, because they are polynomial, right? There is no field behavior here. All are basically polynomial and they commute among themselves. That's why the statistics property, if you see in the last lecture, they are just added up. This is e to the power a times e to the power b, here just e to the power a plus b. So there is no operator property here. It's just this thing. And that's why you don't get operators, you get polynomial, which are basically just variable. Yeah, that's the equation of motion we are taking care of. They do the same job. That's as I said, the IBP and equation of motion are taken care of. Yeah, yeah. That's taken care of. That. Okay, for non-linear relays, it has been modified actually. Okay, so there is a construction of the Hilbert series for the Higgs effective field theory, Carrel effective field theory. Only thing basically you have to be worried about how to put those representations, but the definitions, the space-time symmetry dealing, they're basically same. It's only the what is the symmetry and how you write their representations of pions and all those things. Yeah, but the algorithm is really the same, picking out those simple poles residue. Yeah. Mass dimension you are talking about? Yeah, I'm coming to that. But up to this part, any question? All the interaction, in fact, from the dimension 4 also you can generate actually. Yeah, so what you will get in this formalism, you get a psi square phi. That polynomial you will get. Okay. Now, yeah, no. So what I'm saying, this is the exponential, and that quantity will be integrated over this measure. So in the Hilbert series, when you get the invariant polynomial, in that invariant polynomial, so that will contain some quantity, let's say ni psi square phi. Okay. Now, what you can do actually, if you really, as I mentioned in your while giving the information, if you separately give E, U, D, L, fermion spurion field separately, you will get not only this, but also you'll get, like for example, U square or Q, U, H. In this way, you will get the polynomials actually. Okay, so that is the invariant polynomial you will get actually. Okay. Yes. We are not worried about the failure, but I will tell you how to take care about that. Yeah, but that you can already implement only when there's a covariant form, not before that. Yes. Yes, you can do that thing. Yes, yes, need not to be legal. As I said, that's why the internal symmetry when I mentioned, you can have gauge as well as global both. For example, you can put baryon number and electron number as a global symmetry, right? So then you will get operators which are basically baryon number electron conserving. Okay, but if you know, okay, I want to extract out operators which have certain amount of baryon electron variation, for example, if you want, that also you can do for the global symmetries. You have to scale the measure by suitable quantity actually. Yeah, but you can do that thing. Yes. Statistics? Yes. This is total chi phi.
So there is a covariant derivative inside this.
Yes, exactly. Yeah. So when you calculate the short representations, yes. Any other question? Okay, so now let's come back one by one with your question. Your question was basically, sorry, I forgot. Yeah. Yeah, scaling. Okay, so now what you will do actually, when you are introducing this spurion kind of thing, you define your spurion not by this, by some kind of epsilon to the power delta phi. Okay, so then what you will get, you get a polynomial, and before the polynomial, there will be some epsilon to the power some n, which is a combination of this delta phi plus delta psi, some combinations will be there. Okay, because you know this number for your given field. Okay, by counting the epsilon, you know this is belong to which operator, which dimension operator. So that's the mass dimension tag you just plug in along with this field. Okay, now you see, if your operator consists of 2 phi and 2 psi, okay, what will you do? Epsilon to the power 2 delta phi plus 2 delta psi, and you have given those values, right? Delta psi equal to 1, delta phi equal to, so epsilon to the power 5, and that power will tell you the operator dimension. That's how you can extract that. Okay, that was your question, right? How to know that, okay, where to truncate. So then that's why it's an infinite series, right? And that tells you, now when you perform the integral, okay, then you tell, okay, I want to look into some structures up to epsilon to the power 6. You just, in the mathematics, if you write down, you just pick that coefficient. You can collect all the information with the coefficient epsilon to the 6, you just collect that information, that is your class. Yeah. To the characters. Yeah, but that cancelled actually with that thing. That cancelled with that thing. That one is the coefficient, 1D is sitting inside the character, 1D sitting as a scaling of the character, right? That would cancel actually that thing. Yeah. Okay, so what are the other question? Flavor. Someone has asked flavor question, right? So what you do basically, when you define these fields, okay, you can define how many copies you are introducing. For example, this psi, okay, I'm defining this, but I can say this is basically NF number of fields are there. Okay, so that's how you, again, the way I'm doing the epsilon, so I can put that NF there. And it's a nice way to look at, because some of the operators that involve basically the not only fermion but on the scalar, because when, for example, you have a HHS, how do you get that term? If a 2 doublet epsilon AB, antisymmetric part, and it's a singlet, so that becomes 0, right? Similarly, what you can do in the fermion sector, if you introduce the flavor, some of the operators exist only when its flavor is more than 1. Some of the operators vanishes exactly identically when your flavor is basically 1. And this method is so beautiful. When you calculate them, you will find out those operators coefficient actually proportional to their factors times NF minus 1. So their antisymmetric property and all those things will be taken care of. Non-trivial representation means? Yeah, so you define that as a symmetry.
You have to define it as a
Yes,
symmetry.
exactly. Yeah. You define as a symmetry.
Rather than copies.
Rather than copies. Yes. If a non-trivial one, exactly. Like the global symmetry, you introduce that, and their invariance will take care about this quantity. Yeah. No, CP character automatically will be there. The reason is basically we are working in SU2L cross SU2R, right? So you have L and R. So then, what is the definition of this thing? FL mu nu is basically your F mu nu plus I F tilde mu nu, and FR mu nu is F mu nu minus I F tilde mu nu. Okay, so you have, so that's why what you do basically, you get all the polynomials in terms of FL and FR. Okay, so F, again from this convention, let me put this X, XL and XR, right? So now that's the covariant thing actually I will show also. That when you try to convert them in terms of now the in so-called Dirac representations, okay, you get back these structures. Yes, so you get basically FF tilde term. So you will get a polynomial which looks like a FF tilde. Yeah. If it's allowed by symmetry, it will spit out. Yes, so for that actually, you have to identify first how much lepton information you want. Right? And if you do that, exactly as a global symmetry. So basically like there I was giving a quantum number. Na? So what you do, you just extend that symmetry by E1B times E1L. Right? And then it will have some information. You write down their characters as well. Okay? And then extract that information. Because if you remember, the first day when I write down the Hilbert series in terms of 5 star 5, the invariant term was coming as a simple pole, but there are terms in the polynomial which violates that thing, right? And the deviation from the invariant quantity, how much? By the amount of charges that there, 1 by z square, z square. If you see the polynomial, if you assign them a single 1 unit charge, the coefficient of z before that was exactly the power of the violation. Now, if you scale by that, then that quantity will be appear as an invariant. Okay, yeah. Okay, before going to the covariant form, any other question? Yes. Yeah, basically you use the residue theorem, because all the integral measure eventually reduce into n variable of residue theorem, which are independent. So which one you are doing earlier or later, it doesn't matter, right? Okay. Any further question? How many class means basically? Yeah, that's what I said. So yes, so that will be that coefficient will be given to you, and that is the polynomial actually. So then actually you have to convert them. For example, as most of you are familiar with type 2 CISO, right? SU2 complex triplet. And as we know that in the standard model we have only one quartic term we write down. But if a complex triplet, we have so many terms we can write down, because there are multiple ways to contract them and all are independent way to do, right? So if you use this method, what this will give you? This will give you 4 times delta to the power 4. That means these 4 delta fields can be contracted among themselves in a 4 independent ways, and all the terms should be in your potential. So that's why when you try to write a new Lagrangian, even forget about the effective field theory, you try to write a new Lagrangian for some higher representations, you can just cross check once. Are you accommodating all the representations, or you are sometimes you can write down more which are not possibly true. Okay, up to this part. So then let's move to the real field space. Okay. So now polynomial to covariant form. So the basis that we are working on a standard model gauge group and SU2L times SU2R, right? So my gamma mu is defined as a dot mu sigma bar mu alpha dot beta, gamma 5 is minus. I hope now you are familiar with dotted and undotted indices, so that's why I'm using them. Okay, sigma mu is I sigma bar mu is I minus sigma I. And fermion will be written in a 2-component spinor. So chi alpha is I dagger alpha dot, and psi bar is psi dagger gamma 0 is epsilon alpha chi alpha dot dagger. So this is my left-handed object, and then psi r is sorry, this is now my psi l is chi alpha 0, psi l bar is 0 chi alpha dot dagger, psi r is 0 dagger alpha dot, psi r bar is psi alpha 0. So in this way we can define the 2-component notation. For the field tensor, it's a half x mu nu minus x tilde mu nu and x r mu nu is half x mu nu plus I x mu nu tilde. Okay. So representation wise, phi is transforming as 0, 0, psi l as half, 0, psi r is 0, half, d is like a bispinner, xl is 1, 0, xr is 0, 1. Right, so I have written down all my fields in this way. So now any operator will be in this particular form: phi to the power p, psi l to the power q1, psi r to the power q2, d to the power r, xl to the power x1, xr to the power s2. So this is the generic form of an operator, right? So where we have all these informations. Now if the operator has a mass dimension d, so what we can write down d as p plus 3 by 2 q1 plus q2 plus r plus 2 into s1 plus s2. Okay. So now when you do this computation of the series, you may encounter some kind of symmetry invariant terms, okay, but they may not be useful. For example, the terms which are total derivative, right? What kind of terms are there? For example, d square, which you can write down as a d mu, or more non-trivially phi square d4, which you can write down as a d mu, d nu phi, d nu phi. Okay. So these kind of terms are basically discarded because they are total derivative terms. Okay. Also, you may have some term like d square xl plus d square xr. Why these kind of terms are appearing? Because they are invariant. So whatever invariant, the polynomial will give you. Okay. This is physical or not, that you have to decide based on your field theory knowledge. Okay. So this you can write down as a d nu x mu nu plus d nu x tilde mu nu. That's a total derivative term. So those will be gone. If you have the term, for example, because you are working on a while basis, so what kind of terms you will get in a bilinear? Psi l square, psi r square, right? Now, the psi l square, psi r square, when you have, how do you write down them? Either you can write down as a psi l transpose c psi l or psi r transpose c psi r, right? Or you can write down in this particular form, right? So that's why when you, so this is the polynomial form and this is the covariant field theoretic form that you are writing. So that's the how you will translate. They're also depending on like transpose R C sigma mu nu psi L or R, right? You can have this kind of bilinears also. Now what will be written? So if you can see, if this is appearing, of course sigma mu nu will not be appearing in your polynomial, but this will be accompanied by, let's say, some other quantities which have some Lorentz index. Right? For example, if this has to be contracted, then at least d nu is there. So now automatically when the d nu is there, then you may understand, okay, this kind of operators are basically being generated. Okay. So that's why you have to be keep thinking that, okay, what are the possibilities, and then look at the what are the accompanying fields are there. They are transform indices. Yeah, I'm coming to that. Yeah. That's why this is one of the possibilities. Okay. When you have a psi L, psi R, then you have possibilities psi L bar, gamma mu psi L. or psi r bar gamma mu psi r. That's the only possibility you can have. Okay. Now, if you, whenever you have this kind of structure, this you can automatically write down unique way, x mu nu tilde x mu nu. Now it's coming back to your thing. So whenever you have x cells plus x r square, so when you write down this term, automatically this term will be generated in your theory. That's why they are there. Until for some physical reason you have to add on some kind of additional symmetry to constant them. Otherwise by default they will be there. Similarly now, if you have xl cube, xr cube will be in the polynomial form, and if you write them down, what you will get, mu k xk mu plus x tilde mu mu k xk mu. See, now when we get this kind of structures, right? So this and this will be there. Now you know this is a CP conserving part and this is the CP hurting part. That's why symmetry, internal symmetry and the kind of symmetry we are talking about, they treat both the terms on the same footing. That's why they are appearing in your theory in a pairwise. Okay. So now, this, if you see there's some kind of antisymmetric structures are there. Once you switch on basically their internal symmetry indices, right? That's why this kind of terms, what level? For example, U1, will you have this kind of term? U1 you will not have this. So that's when the Smith operator when you write down this x cube class. Okay, you have for the SU2 and SU3 sector. Right? So that's why this much information if you use, you can reconstruct in terms of your all the filthy operators. If you have a polynomial which looks like a d square xl square, yes. That's why you don't get that part here. Because the antisymmetric property of the generators, when you write down for the SU2, SU3, there's the IJK index that is taken care of by some epsilon IJK. And that's the whole term basically becomes symmetric. That information is already there, yes. So now you have a d square xl, let's say, okay? So which you write down as a d mu x mu nu whole square, okay? So that's basically you can see this give you a current, right? So current kind of term, right? So this kind of structure later we'll see when we talk about the 4 Fermi theory, okay, or psi to the 4 operator, there is some kind of redundancy. So either you write down this operator in a particular form, either that or this one. That will be taken care of. So now you can have a xl phi square d square, which you write down as a d mu x mu nu and then phi d nu phi. Okay, so this is the only way you can, sorry, this is the mu nu. You can extract them out. Okay, okay. So now about the equation of motion, as a one explicit example I wanted to tell you about the psi lr gamma mu I d mu psi lr phi dagger phi. Okay. So if this operator you are writing, okay, then you can write down this operator also. Okay, let me define here. I d double arrow is I d nu minus I d nu from this thing. Okay, so now you see these both the structures have same number of psi, phi and d, psi square, phi square, d, right? So then you polynomial wise you get psi square, phi square d, right? You can write. Now the question is you can translate in a covariant form either this or this, right? Both are basically allowed. Now, what are the other class of operator you are writing? Okay, that will also sometimes dictate you to make this choice. How? For example, if you use this one, okay, and you invoke the equation of motion of the fermion, okay, you will generate the operators which are of the order of psi L square phi cube. Because d psi will give you a psi and a phi from the Yukawa, right? Equation of motion. So this will belong to some class psi L square phi cube. So now, if already you have this kind of term in the polynomial, and if you recast this operator in this particular form, then basically you are making a mistake. That will be double counting. So that's why you will construct this operator. Or what you can do, you can remove this class using the equation of motion and you add this 2. So what is the point? Basically, this among these 3, only 2 are basically independent. Okay. So when you have multiple possibilities of like this kind of cases you may encounter, okay, where to put the D, okay, then what you can do in the back of the envelope, you use the equation of motion of the renovable part and then see whether you can generate some other existing class or not. If you are using that, then that is like a redundant structure. So then this you write down in this particular case. Okay. Then another important part is basically a psi 4 class. For example, you can have operator d bar, gamma mu, Ta. T are basically the generators for SU3, D, then Q bar, Ta, gamma mu, Q. Now, if you are doing some, phasing kind of thing and use the relation among these SU3 generators and gamma mu, what you can write down this operator as d bar D, Q bar Q minus 1/3 d bar Q, Q bar D. Okay. So now, when you write down this d square q square polynomial, you will get at least 2 before that. So if you get the polynomial, you get 2 d square q square. Why? Because among these 3, only 2 are independent. Though each belong to d square q square class, but not all are independent. That number is basically taken care of by this method, and then you know why? Because the same structure you can get 3, but not all of them are independent, only 2 are independent. So that's why these numbers are basically important. So either you write down these 2 operator or you write down these 2 operator, these 2 operator. And this choice will not affect you. At the eventually when you calculate your physical quantities, that will be independent of your choice. If all the choices are equivalent. No, when you get the polynomial basis 2, but you can find out, okay, I can write down 3 such structures. That means basically they must be related by one relation. Because this series gives you number 2, you can write down 3. So even if you do not know the relation, that is guiding you to that these 3 structures are not independent. If you do not have that number, you don't have known that thing. That's why it's not giving the polynomial, but also the number of independent structures of the operator that you can construct, that number is also giving even. And that will help you to make that, to forward that mistake. Okay. Yeah, so this is and some more I have written in the notes. Okay, so I'll share with you. But this is more or less the idea of using these principles, how to construct different kind of operators, and things become more and more clumsy when you go for higher and higher dimension because you have more and more fields, there possible contraction, and specifically more trouble you find out when for the derivative operators. because the derivative operator, where to place them, okay, such that they are independent. With the fields is fine, because you can, with the derivative you can have a IBP, equation of motion, okay, that placing the derivatives are more tricky in this business actually, okay. Otherwise, I hope now you guys can calculate the invariant polynomial from that thing. And the reference you can look into our paper on title Group Invariant Polynomial. This is not the exact title, but I don't remember, but if you search in this name, you will find out. And in this paper, one GitHub link is given, okay, what this mathematical program is given. So what you can do, you can check different kind of representations. There are a lot of examples have been given in this paper, not only Smith, but some imaginary particle and representation you throw, okay, and then construct operator set and this thing, and you can check, you play with that thing, okay. And then if you want to learn more mathematical structures, Brian Henning has a series of paper with Murayama, so those papers also you can look at. Yeah, I think, yeah, that's much I had to say. So I hope I have sent some message. Thank you. No, for example, yes, for example, if you have a, let's say, 4, 5 and 2D, what you have in the D, right? So now, if you have this, so what the Hilbert will give you this number 2, 5 for D2, right? So now you know you can write down this operator as a phi d mu phi whole square, right? And then you can write down phi dagger phi box phi dagger phi, right? Also you can write down as a phi dagger phi d mu phi d mu phi. These 3 independent structures apparently you can write down, right? But here the number is 2. Then they must be connected. And if you check explicitly, that you can write down 1 in terms of other 2, any one in terms of other 2. So that's why this prohibits you to add 3 operators. This tells you add these 2 operator or these 2 operator or these 2 operator. Okay. Yeah.
The statistics already know this because we've already included the space-time character. Like that.
Yeah, that invariance is there, okay. But what I'm saying, that sometimes you have to impose check again in case where you have a multiple possibilities from the same polynomial. For example, this thing.
But the number will be.
Yeah.
Because we have already.
Exactly. So number is fine, but when you try to give the proper covariant form, which form you write down, right? That will be the guideline for that thing. Yes, but number will not change exactly. Number is the guideline for that.
Yeah, so number will not, because we have already included the space-time.
With all those symmetries effectively in this, you have encoded. Yeah. From this, I don't remember exact number, but if this is the 2 upper possibilities are there, then you should get only 1. Yes, that's what I'm saying, that the polynomial is 1, that means basically you should get 1 operator which is not related to this. No, yeah, so this belong to different class, so this will depend the number depending on how many flavors and all those things, okay. But when you have this operator and this operator both in the polynomial, okay, and if the number is 1, that means basically you should write down this operator in a covariant form, not this one. If you write down this operator, that means effectively you are writing this operator.